Hello everyone, I again welcome you all to my new video on thermodynamics, and this will be the last lecture on the chapter thermodynamics. And if you haven't watched my previous lectures, I would recommend you to watch them through the I button that is on the top right corner with the help of the playlist. So uh, before watching this, it would be very helpful if you watch the previous lectures. So let's start without wasting much time. So today we'll be discussing about pure substances. Uh, this is very important topic considering the numericals part, and this will be very helpful and majorly used concepts that are used in numericals will be covered here. So let's start with some new terminologies. This is a TS curve, and here you can see a curve, and this curve divides the region into three spaces, which one considers subcooled region or the liquid region. Here it is saturated liquid, and this part is saturated vapor. uh, like this line represents saturated liquid, and this line represents saturated vapor, and here it is subcooled liquid, and here it is super saturated or super heating region. And in there, like the between the dome region, here consists of both like vapor and liquid parts, so we call it as a wet region. And this line that is going here, this is a constant pressure line. And you can note one thing here, in the dome region, it is a straight horizontal line, because while changing the phase, like the temperature and pressure remains constant, so you can see it here this way. And this is a critical point. This critical point is of importance. Like here, it is a point where the water directly converts from its liquid form to vapor form uh, without this procedure, like without any phase change. So directly converts to vapor, and we call it as critical point. So critical point. Critical pressure at critical point. The critical pressure is 221 bar, 221.2 bar, and critical temperature is 374 degrees Celsius. One more term is there's degree of superheating. So it is nothing but like this is saturated line. Like uh, at this line, all the water is converted to vapor. So if you go beyond this point, suppose from point D, that is on saturated vapor line, uh, you go to point E. From point D to from point E to point E, then this increase in temperature is called the degree of superheating, and same for degree of subcooling or undercooling. You from point A to B, the temperature difference between the point and the uh, for the same pressure, the point that it will be on the saturated liquid line. So uh, point A and point B have the same pressure. So what will be its temperature when it is on the saturated liquid line? So that is temperature at point B. Then its difference we call it as degree of subcooling or undercooling. Superheating, it is a process of increasing the temperature at constant pressure or above saturated vapor line. So this is saturated vapor line, and beyond this you go, you will get the superheating region. And uh, so this is a superheating region, and similarly subcooling is there. It is a process of decreasing the temperature at constant pressure below the saturated liquid line. So in the left hand side of this line, we call it as a subcooling region or subcooled region, and the more decrease in the temperature, uh, you call it as a subcooling process. And wet region, as I've discussed, the part between the dome where both water as a liquid and vapor form are present. Critical point is where directly water converts to the vapor without any phase change. So enthalpy of vaporization at critical point is zero because there is no phase change. Therefore, enthalpy of vaporization is zero. This is important term, that is dryness fraction. Uh, like it is defined as the ratio of mass of vapor, like in a container. It is the ratio of the mass of the vapor present to the total mass of the mixture. So that is we call it as X or dryness fraction. And suppose X is 0.20. So at if in a container it is all vapor, then X is 1, and if it is all liquid, then X is 0. And then what does X equals to 0.2 means? It means 20% mass by mass is vapor and 80% by mass is liquid. So this is a mathematical form for X. It is basically just the, like, you are doing the linear interpolation here. Like, the line is straight and you only want to know, like, you have X or you have the mass of vapor, and also you can find out at which point the line is, like the point is there on the line. So at saturated liquid X is 0 and at saturated liquid X is 1. Okay, and yes, one more thing is there. There is like in this region you cannot apply this ideal gas equation because you cannot consider liquid particles as ideal gas. You can consider vapors above saturated line as ideal gas. So you cannot apply this ideal gas equation in the wet region, and you have these terms to use for this region. We'll discuss it one by one. Yes, but one point to be noted is F here is saturated liquid and G here denotes the saturated vapor. So whenever we talk about F in the subscript, it means that it is on this line, saturated liquid line. And whenever we talk about G, it is about this line. And HFG is the difference here. So HG at point D minus HG at point D. We are talking about point D always. Minus HG at point HF at point B. Because it is also positive line at point B will be equivalent to HFG. Okay. So G here denotes the saturated vapor line. So the reference state in the steam table, we take it U, that is internal energy, specific internal energy rather, and S specific entropy as 0 at triple point of temperature 0.01 degrees Celsius of water. So we need to take some reference because we cannot find the exact value of U and S. Therefore, we take reference point to be at triple point of water. So you can see the expression from here. HF is at HB, as I said, and saturated vapor line is at D, so HG equals to HD, and wet region is, you can write it like HEB plus X times HFG. X is for point C, and HFG is the difference between this. So how much of the difference enthalpy has gained, that represents the X, and HFG can be written like Hg minus Hf. And H is superheated region, that is HD, and you can apply like as you apply for ideal gas, To find the energy, Cp delta T, we can apply because it is a superheated region. So Ht plus Cp delta T is achieved. Similarly, for Ha, is this point, also Hb minus Cp Tb minus Ta. So for liquid, you know Cp, then you can, temperature difference, then you can subtract because it will be having lesser energy than the energy that is at point B. So we are subtracting over here. Similarly, for entropy, notations are basically similar. You can read it. I will be providing all these notes in the description link. You can access it from there. Now let's discuss how to use steam table. That will be useful uh, while doing numericals. So you need to consider, like you need to note the pressure is in bar, temperature is in degrees Celsius. If you are using the steam table that I'll be providing in the description link, then and specific volume in like meter cube per kg, and all things are in specific. So these are per unit kg mass, and the like energy of unit of energy is kilojoule per kg. So you need to consider that. Suppose you need at least two parameters to define any state. So suppose you get uh, mostly you'll be getting one of pressure and temperature and another of anything of the given values like specific volume, specific internal energy, specific enthalpy, specific entropy. And one thing to notice here is that if you get, suppose you get pressure and temperature as the parameters, then uh, if the pressure, suppose you get pressure as 0.7 bar, and if the temperature is higher than 90 degrees Celsius, then it is superheated because in the phase change or in the inside the dome there is constant pressure and temperature, and outside the dome it is constant pressure but temperature is not constant. So if temperature is higher than the temperature at the saturated point, maybe in the liquid or the vapor line, then it means that it is a superheated region, else it is a subcooled region. So if you get pressure and temperature, like if you will get the parameters as only temperature and pressure, then definitely it is outside the dome because you cannot find the value of x with just temperature and pressure as a parameters. So it must be then superheated region or subcooled region, and you need to work accordingly. Like you know how to find enthalpy because Cp for subcooled and superheated, so you need to do by that way. And in most of the question you will be getting one of the temperature or pressure, and another is some of the value from other tables like specific volume, internal energy, specific enthalpy, specific entropy. Okay, suppose you get some, like at you get the pressure is 1 bar and you get some uh, value of internal energy, specific internal energy as suppose somewhere between 417.9 and 250.34, then it means then that it is somewhere between the dome in the wet region. So you can find x. How you can find out x? Like I have given you the equation that I showed you earlier here. uh, Here it is not mentioned for uh, internal energy, but yes, let's first see. You can, like it is mostly the same for internal energy and entropy, so you should use this formula. Like SC, that is at point C, the entropy, SB, that is SF, SFG at difference of SG and SF. So this is SFG and you can find X. So this way you can find X, and this is same for all things. Like the formula is same, just you need to replace. Suppose you are taking H, or you are taking U, or you are taking V, internal specific volume. So the procedure is same to apply. And in this table, it is also we have also for superheated state. Yes, this is for superheated state. You just need to know pressure, like you know masculine pressure and temperature, then or anything else from these values, like uh, in the earlier case also, where you know suppose you get the entropy and pressure as the parameter, and if the entropy is greater than Sg, Sg means the entropy at the saturated vapor line. If it is higher than that, then also it is the case of superheated part. Okay, and same for other also. So you know pressure, suppose you know pressure or some value of P or anything, T or H or U or S, then you can directly get, suppose you get P as 10 kPa and uh, T as 150 degrees Celsius, then you can find any other value. And suppose if you know pressure as 10 kPa, you get pressure as 10 kPa and you get uh, temperature as 175 degrees Celsius, then you need to do linear interpolation. So I hope you must or you all know how to do linear interpolation. You need to use these 2 points, like P at 10 kPa and temperature 150 and 200. You will get the slope of the line. Then by using this slope, you can find the value of uh, find the value of like you can get the value of anything like specific volume or specific internal energy or enthalpy or entropy by, like, because you know the value of the temperature, you just need to find another parameter when you use the slope of the line, like just like y2 minus y1 upon x2 minus x1 equals to y minus y1 upon x minus x1. So you know x is the temperature, like defined by linear interpolation. So in some cases, it might also happen that you get pressure also something else, like that is mentioned here. Like it is mentioned 10 kPa and 50. So you might get 25 kPa or 30 kPa. Then again you need to do interpolation, but then you need to do interpolation twice. Like you'll be doing suppose you get the temperature as 175 degrees Celsius something. Okay, so then you need to first do the linear interpolation and get the temperature at 10 kPa for 175, then at 10 kPa, then at 50 kPa at 175 degrees Celsius. Then you'll be getting one thing constant, that is temperature, that is 175 degrees Celsius. Then you need to do again the linear interpolation for pressure, like varying the pressure. So you need to make constant at least something before doing the linear interpolation, final linear interpolation, and then you can do by this way. Okay, so here the here the extended part, like at 40 45 bar and for pressure and temperatures. So you can use the steam table while doing numericals. And so here we can end this lecture, and I hope by this time you are able to do all like you are able to get all the concepts of thermodynamics, and you are able to do questions. And if you feel there is any doubt or any topic that is not covered, feel free to write in the comment section, and I'll be very happy to make uh, make a video on that. Till then, bye bye. We will see you in next lecture.